Hi, everyone. We're continuing with these new trig identities, starting with the three sum identities. Now, this was a favorite meme of mine early on, back in chapter 0, looking at the bottom two panels, pointing out the square of a plus b is not a squared plus b squared. The square of a sum is not the sum of squares. That makes teacher mad. Hopefully not this mad. I once had a student wonder if that was blood over there. No, that's a cloud, not blood, please. But remember, the square of a sum is not the sum of squares. Squares do not distribute over sums. The same is true for sine, cosine, and tangent. The sine of u plus v is not sine of u plus sine of v, right? So sine and cosine and tangent, they don't, in a sense, distribute over sums. The cosine of a sum is not the sum of cosines. The tangent of a sum is not the sum of tangents, all right? So these bottom two panels help remind us of that. So the sum identities are more complicated, right? Like sine of u plus v, that's the sum of the mixed up products. I'm going to come back to this meme in particular in just a moment. Back to the main schematic. So we have these three sum identities. We had ways of memorizing those. And from those, we got the three difference identities from flipping all the visible signs. In fact, I can write that, type that in small text. Okay, so we flip all visible signs to get from sum to difference. Now, to get from the sum identities to the double angle identities, numbers 7 through 9 at least, we're going to apply a trick. Now, eventually, we're actually going to get 5 double angle identities. There are actually 5 of these because there are 3 for cosine. We'll deal with those later. For right now, let's get to the 3 primary double angle identities, identities numbers 7, 8, and 9. Now, of course, I'm not going to number these all the time. You don't have to memorize these numbers. I'm just being cute here. We're going to end up with 19 down here. All right, what are numbers 7, 8, and 9? So the double angle identities. How do we get the sine of 2u? How do we get the sine of 2u? What is the double angle identity? What is the double angle identity for the sine function? What's an expression for sine of 2u, where we no longer have a 2 inside the argument? Okay, now, sine of 2u, how does that break up? Well, we can use the sum identity for sine, because what is 2u? If you asked an algebra student, hey, what's 2u? A good algebra student would say, well, 2u is u plus u. So we can basically apply the sum identity where v equals u. So in the overall schematic, in the overall schematic up here, to get from the sum identities to these 3 double angle identities, the main ones, the key trick we're going to use is that we're going to let v equal u. Let v equal u. And we can derive these. All right. Again, the sum identity for sine is to sum the mixed up products. Although since v equals u, they're not so mixed up. Sine of u, cosine of u, plus cosine of u, sine of u. In fact, take a look at these two terms. If you do a snap substitution, this basically looks like xy plus yx. These two terms are like these. These are like terms. These are like terms. Well, back here, how can you simplify xy plus yx? Well, xy plus yx is equivalent to xy plus xy because multiplication is commutative. And what is xy plus xy? It's twice xy, 2xy. Right. Kind of like on this meme, what's a plus a? 2a. What's apple plus apple? 2 apple. What's xy plus xy? It's 2xy. What's this term plus this term? These are equivalent terms. You can actually show that. They're equivalent terms. 2 sine of u cosine of u. So sine of 2u can be written as 2 sine of u cosine of u. And that can be helpful sometimes. Sometimes that 2 gets irritating. Maybe you have an expression where you're dividing this by sine of u or cosine of u, and then you can simplify. All right, so sine of 2u is 2 sine of u cosine of u. The way that I remember this is that it's twice the product. I think twice the product. And that's a reminder. It's 2 sine of u cosine of u. A common error is for students to just pop out the 2 and go home. It's not just 2 sine of u. You also need the cosine of u. It's twice the product. Twice sine of u times cosine of u. All right. What about the double angle identity, the primary double angle identity for cosine? Cosine of 2u is cosine of u plus u again. So again, we're letting v equal u in the sum identities. These match up. Sum identity for cosine. It's the cosine product minus the sine product. It's cosine of u, the cosine product, minus the sine product, sine of u, sine of u. Let's go back to this meme. What's a times a? It's a squared. What's cosine of u times itself? It's cosine squared of u. What's sine of u times itself? It's sine squared of u. So again, a way to remember this, you can still think of this as basically the cosines minus the sines. But here they're squared. Cosine squared of u minus sine squared of u. Cosine of 2u equals cosine squared of u minus sine squared of u. We can call this identity number 8. So this is identity number 8. The one up here is number 7. Not that we really have to care. Next up, tangent of 2u. And I have a really hard time memorizing this just from scratch. I really have to go through the sum identity for tangent. Tangent of 2u equals tangent of u plus u. I remember that the sum identity for tangent goes the sum over 1 minus the product. It's the sum over 1 minus the product. By sum, I mean tangent of u plus tangent of u. Put that in blue. Over 1 minus the product. By product, I mean tangent of u times tangent of u. I'll put this in green. All right. How can we simplify these? Let's go back to this valuable meme. What's a plus a? It's 2a. Tangent of u plus tangent of u is 2 tangent of u. Whereas on the bottom, what is a times a? A times a is a squared. What's tangent of u times tangent of u? It's tangent squared of u. And a lot of students mix these up. That's why I kept going back to that meme. A lot of students don't just forget about the fact that this does not equal this. Students forget that this equals this and that this equals this, and it's not switched. A plus a is 2a. A times a is a squared. If you know that, then you should believe that we end up with this over here. Two tangent of u over 1 minus tangent squared of u. Again, I have a hard time memorizing that, but since I know the sum identity, I can get the double angle identity pretty quickly. But make sure you don't switch these. So that's our number 9. So we have now these 3 basic double angle identities for sine, cosine, and tangent. But wait, I promised you 2 more double angle identities for cosine. There are a total of 3 double angle identities for cosine, and they're all useful, including number 8, which we just discussed. But we're going to discuss 2 more double angle identities for cosine. All right. This won't take long, actually. So let's go back to here. So here's our number 8. cosine of 2u equals cosine squared of u minus sine squared of u. All right. Now let's say that we're doing something like solving a trig equation. Maybe we have cosine of 2u. We don't like the 2u. We want to break it up. But I don't like this mix of cosine squared of u and sine squared of u. I might just want this in terms of either cosine squared of u or just sine squared of u, and maybe constants. Well, what key identity can make one of these look more like the other? Mr. Pythagoras, consider the Pythagorean identity. I'm writing this here as cosine squared of u plus sine squared of u equals 1, in part because we're going to apply the Pythagorean identity. And also, notice this, and this is something that confuses students. This may well confuse you on the homework. Remember that down here, cosine squared u plus sine squared u equals 1. But cosine squared u minus sine squared of u is not 1. It's cosine of 2u. So the difference in the signs here, SIG and S, plus versus minus, makes all the difference. This is 1. This up here is cosine of 2u. Flipping the sign changes you from this to this. So watch your sign. With a plus sign, you get 1. With a minus sign, you get cosine of 2u. This will bite you in the homework. Anyway, we're going to apply the Pythagorean identity. See, this is even more confusing. We're going to apply the Pythagorean identity here to help rewrite this expression here. So how can we do that? There are 3 versions of the double angle identity for cosine of 2u. Again, I don't care how you number them, but here's the original. I claim that we can get from here to both here, version 2, and here, version 3. So this was identity number 8. Not that we care, but here was identity number 8. In blue, this here will be identity number 10. We use 9 for tangent of 2u. 10 here. This is in blue, and this here is 11 in green. So by the time we do these, we'll have 11 in the tank. All right. How do we get from 8 to 10 and 11? Remember, 9 was for tangent of 2u. All right. It's applying the Pythagorean identities. Let's go through it. How do we go from version 1 to version 2? Version 1 to version 2. So from identity number 8 to identity number 10, actually. All right. Cosine squared of u is equal to 1 minus sine squared of u. That's a variation on the basic Pythagorean identity. Okay, well, what's 1 minus? I'll do a snap substitution. X minus x. What's 1 minus x minus x? 1 minus 2x. In this case, 1 minus 2 sine squared of u. X was sine squared of u. How do we get version 3, or identity number 11? This time, we replace sine squared of u with 1 minus cosine squared of u. That's another variation on the basic Pythagorean identity. Distribute the negative 1 here. We get this here. In short, it's of the form x minus 1 plus x. X plus x is 2x. Here x is cosine squared u. X is cosine squared u. So we get 2x or 2 cosine squared u, and then the minus 1. So in order to get from this identity in red, number 8, to these identities, numbers 10 and 11, we're applying the basic Pythagorean identity in 2 different ways. Did I write that way up here? Yeah. We're applying this basic Pythagorean identity in 2 different ways. One where we solve for sine squared u, another where we solve for cosine squared u. All right. So if you solve this in terms of sine squared u, solve for this in terms of sine squared u, you get this. If you solve for this in terms of cosine squared of u, you get that down there. So it's from the Pythagorean identities. So to get the 3 for cosine, keep in mind the Pythagorean identities. Mr. Pythagoras. That gets us from 8 to both 10 and 11. Mr. Pythagoras. Can I type Pythagorean? Pythagorean identities. Wow, we've done a lot so far. We've covered 11 identities so far. 3 for sum, 3 for difference, 3 and then 5 for double angle, because we have 3 of these identities for cosine. And in fact, we're going to use number 10 and number 11, these over here, to get the PRIs, the power reducing identities. That's another reason why we did this. Not just so that we could get the right side just in terms of one type of squared trig function, but because we're going to use these two identities, numbers 10 and 11, to derive the PRIs, the power reducing identities, specifically from 10 and 11. And that's next time.